So lecture 4, electrostatics in free space. Now we are ready to jump into actual electromagnetism. And as a first step, we are gonna learn about electrostatics. And as I said before, electrostatics is about stationary charges. So we have charges, but they are not moving at all. They're just stay at a certain position in space. So that's electrostatic situation. And then we are only interested in electrostatics for now. So, and then to make problem even simpler, we first are interested in electrostatics in free space. So what I mean by free space is there's nothing out there, okay? Only the charges exist. So the problem is simple, very, very simple problem. And then lecture 5 would be about electrostatic in materials. Like you can think of glass or metals or other types of material like semiconductors. All those materials, if there's a material, how can we deal with it? That's what we are gonna learn in lecture 5. And lecture 6, we will learn about like special techniques, the mathematical techniques that we can solve electrostatic problems. Okay, so that kind of finalizes the electrostatic statics. Okay, so let's begin the electrostatics in free space. And because you know already many things about this electrostatics, so probably I'll focus more time on you know, the contents that you may not be familiar with. Okay, so let's look. But before then, let's just talk about the units. So you know, of course, we are gonna use SI units throughout the lecture, and then meters, kilograms, second, force in newtons, energy in joules, charges in coulombs, and potentials in volts, and farad for capacitance. By the way, does anyone know what SI stands for? SI? Can anyone type in like what SI stands for? Right, as Jung Chae-yoon said, it's international standard. But why not IS? Right? If it's international standard, it's supposed to be IS, right? Instead of SI unit. Right, okay. You guys know pretty well about this. Okay, Kim Jin-young, as Kim Jin-young said, if you write international standard in French, it's something like standard internation was something like that. I don't know how to do the French, but anyway, if you write things in French, it's SI. So just to good to know. Okay, so Coulomb's law. Everyone knows the Coulomb's law, and then this guy in 1784. Coulomb figured out that there is forces exerted between two charges, and then what he figured out that the direction of the force is along the line connecting these two charges. Okay, and then the amount of force is proportional to charge amount Q1, Q2, multiplication of Q1, Q2. And also inversely proportional to the square of the distance. So R12 squared, like 1 over R12 squared. So in sum, this is Coulomb's law, right? F12 is Q1, Q2, 4 pi epsilon naught, R squared, A R12. And then here, there are some notation that I want to, notational definition here. So F12 means force exerted on charge Q due to charge 1. Okay, that's 1, 2. Okay, so force exerted on charge Q due to charge 1. That's what I mean by this. And then and then similarly R12, which is the displacement vector, is connecting from charge 1 to charge 2. Okay, from charge 1 to charge 2, that's R12. And then AR12 is defined as a unit vector along that direction. And then large R is the magnitude of R12. Okay, and for now, you don't need to worry about 4 pi epsilon naught. 4 pi epsilon naught, this is just a coefficient to match these two relations. So it's not important. Okay. So, and then you can write it in this form. So R12 squared, and then R12 divided by R12 absolute value. So this term is equal to the unit vector, and then R12 squared is just equal to R squared, right? Or in other words, you can just replace R12 to R2 minus R1, right? R2 minus R1. Then it's written like this, right? So everyone knows this, right? Unless you might not know the, I mean, there can be the case that you don't know about this full vectorial form, but at least you know that F equals Q1, Q2 divided by 4 pi epsilon 0 R squared. That's what we learn in high school physics, right? And then if we have many charges, like we have like charge Q here, charge Q at this point, and then multiple other charges, Q1, Q2, Qk, and then if you want to obtain the force exerted, total force exerted on charge Q, all you need to do is to evaluate partial forces, so force between Q1 and Q, force between Qk and Q, force between Q2 and Q, and then just add them up, right? Then you get the solution. So this property, this way of calculating things is called superposition principle. So, and more technical language, we say the system is linear. Because the system is linear, when we can just add solutions by adding them, simply adding them. Okay, so that's that. And then force exerted on Q is just the sum of the partial forces. And then electric field at position of Q is defined by normalizing F by Q. Okay, so electric field means if you have a unit charge at this position, what would be the force that this charge would feel? Okay, so in that sense, the electric field is force field. I guess so far things are easy, but if there's any question, please ask now or anytime, just by typing things in the chat. So now we can, of course, expand this concept like superposition principle into more continuous charge distribution. So we can think of point charge and then line charge with line charge density rho L, or surface charge with surface charge density rho S, and volume charge with volume charge density rho V. So we can do this, right? We know the point charge is doing this. And then for line charge, the infinitesimal charge amount is actually rho dl, right? And then what you need to do is to do rho dl and then take an integration, line integration, in order to get the electric field. And similarly, if you want to obtain the electric field due to surface charge density distribution, you need to perform a surface integral. And similarly, for the volume charge, you need to do volume integration. Okay, so probably so far it's a bit abstract. So what we want to do is to jump in to the actual problems. So let me tell you what we are gonna do. What we are gonna do is we want to solve electric field from infinitely long line charge and also infinitely large charged sheet, and also infinitely and also from a charged sphere by using Coulomb's law. And then we'll move on to Gauss law, another important law in electrostatics, and then redo the same problem again. Okay, so basically what you're gonna solve here is very simple problems, but I hope you learn everything about the theorem or the law. So continuous charge distribution. Let's first do the line charge. And as you can see here, this exercise asks you to find the electric field P, field at point P, right? Due to an infinitely long straight line charge, right? By using Coulomb's law. Okay, and of course we supposed to use cylindrical coordinate system. That might be most useful, right? Then the position of P should be rho phi z, defined as rho phi z. Okay, so that's good. And then yeah, but here it's connected to the origin, so then z is 0. So how do we solve these problems? Well, all we need to do is pretty simple. We need to just write, these quantities in terms of the coordinate variables and or other given numbers. So let's first do say dl. Okay. dl is the infinitesimal line segment of this line charge, okay? And then we call this as dz prime, okay, as you saw here. And then this part is kind of important. We use primed coordinate for source position. This is kind of my convention, okay? In order to describe source position, I use primed coordinate. And then in order to describe position of interest, I use unprimed coordinate. Okay, so let's look at this now again. Then what's R? Can anyone type in the what's R? How to express R with given coordinate variables? What is R? Anyone? Right. Yeah, you guys did a good job. So it's like, so this is R, right? The distance between dz prime and P is R. So so it's like z prime squared plus rho squared, right? And again here, rho is just unprimed because it's about position of interest, but z is primed because it's position of source. And how about AR? AR is more complicated, but you can obtain because it's from source position to the point of interest, and then it's actually is that true? Oh, I'm sorry, AZ. Right. So if you decompose this into z direction and rho direction, you'll see that the rho component is about this much and z component is about this much, right? And then what you need to do is just to plug everything into the equation and then solve. So if you plug everything in, you get this equation. Right. And then here, even before we actually perform the integration, we know that the AZ component vanishes, right? Because the AZ component is odd function. And then we have a even integration range. What I mean is that if you look at the z component is this: z prime squared, rho squared, z prime, right? And then this is even function, this is odd function. So in total, it's odd function. So it's gonna look like something like this, right? It's odd function. It flips sign with respect to the origin. So if you integrate from negative infinity to positive infinity, you get 0 because they have just a flip sign and the magnitude is basically the same. So even before performing integration, we know that the z component goes away. And then you have only rho component, right? And then to perform this integration, you need to apply some technique. So you can just replace z prime as a rho tangent alpha, and then dz prime as rho secant square alpha d alpha, and then this integration becomes simplified to cosine alpha integration, and then you got the answer. So for those who are not familiar with this integration, like a trigonometric change of variable and integration, you can just accept it. Okay, it's not an important point of this problem. So if we take exam, and then if we in that exam, if we have any problem that involves a complicated integration technique, I'll give you integral table. Okay, so you don't need to worry too much about these techniques. These tricks are not that important. What's important, I would say, is just you need to be able to do this properly. DL, R, and AR into proper coordinate variables. Okay, so any questions so far? Is this easy enough? I guess it's not too difficult. So how many of you already saw this problem in other lectures, like elementary physics? How many of you saw this problem before? Raise your hand, please. If you saw this problem before, raise your hand. Many. Okay. Okay, good. Okay, so probably we are doing something too easy for you, right? But I'm just giving you, try to give you a proper way of solving it, okay? So like distinction between source position and the position of interest and everything, this procedure that I want to convey, even though the problem itself is easy, okay? So let's try to do one more exercise, which is this. Okay, now we want to solve charged sheet with charge density rho s. Okay, and then we want to evaluate electric field at this position, 0, 0, h. 0, 0, h. Then how are we gonna solve this problem? Say what would be ds, and then what's r, and then what's ar? These three are most important thing, right? Let's say we have this infinitesimal surface component. Then what is ds? Can anyone answer? What is ds? Let's say this is your infinitesimal surface component. Then what's ds? I guess you know the answer, but just too shy to type in, right? Yeah, well, okay, but there are many different answers. Rho prime, d prime. Okay, yeah. So seems like many of you get the correct answer. So it's like ds is rho prime. So in my notation, it's rho prime d phi prime d rho prime, right? The reason why everything has prime is because we are talking about source position. So we put prime on every coordinate variables. Then what about r? Can anyone type in the r? I guess this is similar to the previous problem, right? So in this case, r is rho prime squared plus h squared, which is g squared, right? This is h, so it's h squared. And then ar we can similarly find. So it's like, if you look at here, the z component is r h a z minus r rho prime a rho, right? So that's the unit vector connecting from here to there. So once you know this, then everything else is just solving integration, which is just straightforward step. So if you try to solve it, this is it. This is the way you solve it, and then so once you plug everything in, you get this. Okay, and you have two components here too, and then we know that rho component is gonna go away, so there wouldn't be any a rho component, and then we know this even before solving the problem because of the symmetry, right? So let's say you have some rho component. Let's say you ended up having some rho component. Then you're having a problem, right? Because even if you rotate the system, everything's the same, right? It's infinitely large sheet. So it shouldn't have any preferred direction except for z direction, right? So it doesn't make any sense that you have rho in the end, right? So rho goes away. And then AZ component survives. And then if you perform the integration, then again, this integration is just a simple integration. If you perform d phi integration, you get 2 pi because it runs from 0 to 2 pi. So you just take 2 pi out, and then you perform like rho prime integration. And here it's rho prime integration is easy. See, you have rho prime squared, and you have rho prime here, which makes it very easy to solve, right? And then you get the integration, and you get this solution, right? Good. And another thing that we want to, I want to mention from this problem was that the dependence on distance. So if you think about this problem, let's say, let's first start thinking about a point charge. And then if your position of interest is the distance between these two is r, then your electric field is proportional to 1 over r squared, right? That's Coulomb's law. And then now you have a line charge, infinitely large, long line charge. And then your electric field is proportional to 1 over rho, not rho squared, right? 1 over rho. Rho is the distance between your charge, your line charge and the position of interest. And then you can also imagine like what's gonna happen if we have a surface charge. The dependence would be 0, no dependence, right? So if you have an infinitely large surface, then as you can see here, your answer does not depend on position, right? And that is because your source dimension increases. Your source dimension was from 0 to 1-dimensional to 2-dimensional. So as your source dimension increases, your dependence, the electric field dependence on the distance would go down, like by factor 1, right? Which makes sense. And so here's my question. Let's say if you have a volume charge, and then if you calculate electric field from the inside, okay, or charges if you want to just calculate the electric field from the inside of the charge, let's say this is the center of the charge and then your distance is r, then what would be the dependence of the electric field to r? How your electric field would depend on r? Would it depend on like 1 over r squared? Or 1 over r? Or not depend on r? Can anyone guess what would be the solution? What would be the dependence? Yeah, so right. So as many of you guessed, correctly guessed, electric field should be proportional to r in this case, because your charge distribution is now 3-dimensional. So we have to go to gain one more dimension. So your electric field should be proportional to r in this case. Okay, so everything is reasonable, right? So I wish you have this kind of sense in solving problems. Like, okay, so let's look at the problem now. If you look at the problem, okay, the dimension of the distribution is like this. So your solution is supposed to be proportional to that, and this kind of intuition is very important in understanding complicated systems in a simple manner. Okay, so so finally, continuous charge distribution. Of course, you can also do the similar job, but I just don't want to do it. But here, what I've give you as an example is that if you want to evaluate the electric field outside the charged sphere, it's actually same as the electric field exerted due to the point charge. Okay, But if you want to evaluate the electric field inside the sphere, then your electric field is proportional to R. We will learn about this in Gauss theorem again. But anyway, in this example, because your position of interest was outside the sphere, it's just proportional to 1 over R squared. Okay, so any questions so far? I guess this is easy, right? You already know about Coulomb's law, and you know all these examples probably beforehand. And but still, I think it's reasonable to cover this topic just for completeness. And probably you miss some of the important points when you learn this first time. So I just want to recover this. And so let's move on to Gauss' law. Okay, so Gauss' law states this. So what I mean by this is E dot ds, if you perform a surface integral of E dot ds, this is equal to the amount of charge enclosed by the surface divided by epsilon naught. Okay, and this is equal to, so in differential form it looks like this: divergence of E is equal to rho divided by epsilon naught. Okay, so if you integrate volume integration, perform volume integration on both sides, due to the divergence theorem, you get this. Okay, I guess everyone knows about the Gauss theorem. Just to double check, does anyone never heard about Gauss theorem before? Please raise your hand. This is first time you hear about Gauss theorem. Please raise your hand. Okay, so it seems like everyone already knows about the Gauss theorem. So another question I want to ask is that, so when did you learn the Gauss theorem? Did you learn in high school, or did you learn this in elementary physics, freshman physics class? High school, please raise your hand. High school, learn Gauss theorem in high school. Please raise your hand. 1, 2, 3, 4, 5. Oh, okay. Okay. Seems like almost 15% learned Gauss theorem in high school, and probably the other 85% learned this in elementary physics. So yeah, because you all familiar with this Gauss theorem, I don't want to, just simply repeat what you already know. Instead, I want to focus more on what I think is important, which is symmetry argument. So let's begin the Gauss theorem and apply the Gauss theorem for the problems that we already solved using Coulomb's law. So here, the simplest problem. So everyone knows that how to apply Gauss theorem here, right? So in order to apply Gauss theorem, what you need to do is to first determine Gauss surface, right? And then it depends on, and then you can choose any Gauss surface. But the thing is, in order to make your problem easily solved, you'd better choose your Gauss surface in a smart way. And then you know that for this problem, it's better to choose spherical Gauss surface. Okay, so let's say you have a spherical Gauss surface like this. Then the Gauss theorem states E dot ds is equal to Q divided by epsilon naught, right? And then for spherical surface, ds is what? ds is all along like AR direction, right? It's all AR direction. So what you ended up having, and then due to the symmetry, because there's nothing change, even though you rotate the system, you know that this integration becomes ER 4 pi r squared Q divided by epsilon naught, right? And then ER is Q 4 pi epsilon naught r squared. That is probably the story that you know, right? You are familiar with. And then here you already apply one symmetry argument. That is, we ignore the dependence of E on, say, theta or phi. So we here, from here to here, we just assume that E is not dependent on theta or phi, right? Otherwise, you cannot solve this problem, solve this integration easily. So how do we know E does not depend on theta or phi? I think that's a relatively easy symmetry argument. Like E, so E does not depend on theta or phi. How do we know it? Yeah, that's symmetry. Yes, that's spherical symmetry. That's true. But the important thing is, yeah, like, okay, so let's keep that in mind, and then I'll ask you another question then. Another interesting question. So from that argument, you know ER, right? And what about E theta or E phi? How do you know there's no E theta component or E phi component? So thinking about your EDS Q epsilon naught for the spherical surface, because your infinitesimal surface component is along AR direction, even though E has non-zero E theta or E phi component, it wouldn't apply. It wouldn't affect the integration value, integration result, right? So this itself doesn't tell you anything about E theta or E phi, right? There's no problem that you have E theta or E phi non-zero component. Gauss theorem still holds. So you need an additional argument to rule out theta or phi component. So what's your argument? Let's say you have E theta component, or let's say you have E phi component. What's wrong? Can anyone answer this? I mean, you know, like your gut feeling, right? I mean, you know that it's kind of something's gonna wrong, like if you have theta or phi component, right? So you can kind of naturally, intuitively rule out that possibility. But the thing is, Gauss law itself doesn't tell you anything about that, right? Gaussian law itself does not tell you, ensure you that there's no theta or phi component. No charge along that direction. 송민차, no charge along that direction. What do you mean? Oh, so yes, I understand what 송민차 said, but this answer is kind of assume Coulomb's law, like assuming that we know Coulomb's law, right? So Coulomb's law says that the force only exerts along the line connecting two charges, right? But let's assume that we don't know Coulomb's law, but only the Gauss law. Then can we still say anything about E theta or E phi? I think this is the key point in applying Gauss law, because Gauss law does not tell you about these components, but we somehow just assume that E theta and E phi are 0, which is not logical actually. It's not like grounded. So let me tell you the argument. So when you want to do symmetry argument, you always need to think about symmetry operation, okay? And then you know, proves that you know, something's gonna wrong if symmetry does not hold. So let me, in this case, let's see what would be the proper operation. So let's say you have, say, some other components, E theta or E phi components. Then the proper operation that I think is most efficient is you take this axis as your center of rotation and then rotate a little bit. Okay. Now, if you compare the situation before rotation and after rotation, the position of the Q, charge Q, stays there, exactly same. And then position of interest is exactly same. So the system is exactly same, right? Before and after rotation. But your solution, right? Let's say you have some E theta component or E phi component will be rotated by this rotation angle, which is contradictory, right? The system is exactly same, but your solution is different, which cannot be the case. So because of this, you know that you cannot have any E theta or E phi component, right? So when you apply Gauss theorem, I hope you keep thinking about this symmetry operation. Okay, I think it's not a good practice to simply say bisymmetry, because bisymmetry can mean many things, right? And then it can be, you know, there are some cases actually, symmetry gives you some unintuitive answer. So not just by saying symmetry, but like thinking about the actual operation that that you want to apply. Okay, so that's that for point charge, and then let's move on to yeah, here if you look at here too, by spherical symmetry, E is ERAR, right? It's pretty simple statement, right? And then this, I cannot say this is wrong, but this is not enough, like not detailed enough. So in order to rule out other possibilities, you need to think about the actual symmetry operation. That's what I recommend you to do. Okay, so let's do a similar thing here again. Now you have a line charge, right? You have a line charge, and then you want to evaluate electric field at this position. And then we know that the cylinder is the best choice for Gaussian surface. Well, that's true, of course. And then about we have to determine two things. One is E components, like E can have E rho component, E phi component, and E z component, right? And then each component can depend on rho, phi, z. And then, this is easy to know, right? So like in this case, nothing can be dependent on z or phi. Everyone agrees upon it? Like any E field component cannot depend on phi or z. Why? Because it's easy, right? In order to know that, if let's say you do a z translation, like you translate this entire system by z, because everything is here. If you move your system by z, basically everything's are the same, so it cannot depend on z coordinate. And similarly, due to the azimuthal rotation, if you apply azimuthal rotation, you know that it cannot be dependent on phi. But rho, it's different story. So everything, all these components can depend on rho. So that's one symmetry argument about the dependence, and the other one is about the component itself. So E rho, E phi, and Ez. Which one is possible? Like which component is possible? And which component is not possible? I guess you already know the answer, right? E rho is the only possible, only non-zero component, and E phi and Ez are zeros. And that's what you know. But why? What's wrong if you have Ez component? Let's say you have Ez component. Then which symmetry, which operation reveals that this is not, reasonable? So in other words, what's wrong if we have no non-zero Ez? Anyone? If you have any ideas, please type in. Yes, yes. So these are all reasonable answers, right? As Kim Yu-il and Park Se-hoon said, we can basically flip the system upside down. So like, along this, let's say this is your reference line, and then flip it. Then charge distribution is exactly same. Point of interest doesn't move at all, but your answer flipped, which is not reasonable, right? It cannot be the case. So Ez should be 0. Then what about E phi then? How would you argue that E phi is 0? So let's say we have E phi here, E phi like this. What's wrong? Park Jun said, I think flipping could work again in this case. Like how? Okay, so there are two answers. Some people says rotating by along z-axis, rotating with respect to z-axis. And some people says flipping. I would say rotating is not the correct answer. Because if you think about, let's say you want to rotate, because it's azimuthal, you may easily think about rotation with respect to z-axis. But you know what? If you actually rotate this thing, your position of interest is now in different position, right? So it's not at the same. It's not the same problem, right? Because your position of interest changes. So yeah, and as Park Jun and Park Seun said, again, flip it. Okay, if you flip it, you will see this is not gonna. Yes. So here there are many. Actually there's the answer is just not one, but the answer that I like is this. Let's say just flipping upside down again, and then this will be changed to this direction. And it's not gonna work. So I guess actually this is pretty much all I want to say. And then the rest of the calculation, I guess you are already familiar with, right? So once you are sure that electric field can only have E rho component, and this E rho component can only depend on rho, then everything else is just easy, right? Just you apply a Gauss theorem and then just evaluate E dot ds, which is equal to Q divided by epsilon naught, and then Q is rho L multiplied by L, right? So E is along rho direction, and then this dependence has this dependence. Any questions so far? This is easy enough, right? Like, you know, but I guess it gives you a new perspective, right? Even though you already knew about Gauss theorem, but probably you focus more on this part, evaluation of electric field flux and Q. But I would say this is just trivial thing, and what's more important is to ruling out the possibilities. Like this is more important. Why this is the case? Knowing that is much more important than evaluating this. Okay. So let's try to do another one then. Another one. This one. The same problem. And so here we typically, so infinitely large charged sheet, and then if this is your point of interest, you typically set your Gauss surface either like this or like this. Anyway, is fine. And again, here what we need to do is to determine two things. E can have E, E rho, E phi, E z component, or X, Y, Z, whatever it is. And then also the dependence of each component. And then again, dependence is easy. We know that all these components can only depend on Z, right? Because XY, we have XY translational symmetry. So if we like translate XY, the charge distribution doesn't change. So it should not depend on X or Y. But Z is like independent coordinate. So it can depend on Z. But you know, in the end, if you actually solve the problem, it's not even depend on Z, but we cannot rule that out from the beginning, right? So EZ is possible. And then we need to talk about the component, like whether E rho and E phi components are possible or not. And then EZ is possible. So how to do this? How to know whether E rho or E phi is impossible? Can anyone have an idea? Which operation prevents E rho or E phi? Anyone guess? Rotation with respect to Z plane. I mean, there's no rotation with respect to Z plane. Rotation should be done with respect to some axis, right? Z axis. Okay. Okay, there are many interesting answers actually raised. And by the way, rotation with respect to just the z-axis, it shouldn't be the case, right? If you do the rotation with respect to the z-axis, then position of interest also moves. So I guess you probably mean about rotation with respect to the axis parallel to the z-axis, but passing through the point P, right? So this axis, if you take any rotation with respect to that axis, then the system itself remains the same. The position of interest remains the same, but you know the solution changes so that it's contradictory. But anyway, you get the point, right? You get what I wanted to say, like throughout these examples. So what's important is you have to sharpen your symmetry argument. You cannot just say that, oh, by cylindrical symmetry, by spherical symmetry. That's kind of very vague term. So in order to actually be able to rule out these possibilities, you should be able to pinpoint like which operation induces contradiction, right? And so as a result of that, you have only a few components of your electric field. So now you know that your electric field can only have Z component. Then the rest of the step is just applying Gauss law. And then because the electric field is proportional, is parallel to the Z axis, right? So all the side walls does not contribute in integration. Only the top surface and bottom surface contributes. So which is 2 EZA. And then the enclosed charge amount is rho S multiplied by A and divided by epsilon 0. And you get electric EZ component, which is this rho S divided by epsilon, 2 epsilon, right? And again, as a result of calculation, you finally know that E does not depend on Z coordinate, but you cannot know this beforehand, right? You cannot rule out this possibility by just doing symmetry argument, right? Okay, so I guess this is enough for today.